Hello, my name is Jessica Salinas. This is my molecule called cysteine. This is a presentation for Chemistry 2423, Organic Chemistry 1. So why is cysteine important? Cysteine is present in large amounts within both our hair and nails and as well as the rest of our body. It plays an important role in white blood cell activity and can also be found being helpful as a powerful antioxidant. Some of the health benefits of cysteine include detoxification and the production of collagen, which collagen is part of what makes our skin so elastic and helps in texture. Medical use. The supplemental form of N-acetylcysteine, or NAC, has an important role in our bodies because it is the precursor to make glutathione, which is a powerful antioxidant and protects our cells from oxidation. And NAC, or acetylcysteine, being a human manufactured molecule, that means that it can become more concentrated in dose and better serve this job of being an antioxidant. General information. The molecular formula of cysteine is C3H7NO2S. It is found in animal proteins like dairy and pork, thus I have added the cow in the corner, and plants like broccoli and onions. It's not able to reach a boiling point because by the time that it would reach a boiling point, it has already decomposed. So there is no boiling point to be recorded, but there is a melting point, or the point where it decomposes, which would be 240 Celsius or 464 Fahrenheit. Cysteine is highly soluble in water because of its ability to bond or interact with water molecules. It is also considered highly reactive because of its weak bonds, which are easily breakable. Hybridization. Over here, we have a thiol group or thiol group containing the sulfur. So we are going to call this sulfur. And it is a sp3 sulfur with a bond angle of 104.5, making it bent in molecular shape. It is considered sp3 because it has two bonds that it is connected to, which is our hydrogen and the carbon that it is connected to. And this would usually make it sp, but because it is a sulfur, that means that it contains lone pair groups, making it sp3. Over here in the green, we have NH2, and we are going to call it our nitrogen group. And this is also a sp3 group with a bond angle of 107, making it tetrahedral. And this is a tetrahedral group because it also has a lone pair group, but it has three bonds that it has. The two hydrogens that it's connected to, and the other carbon that is connected to. In the purple, we have the OH group, or we are going to call this our regular oxygen group, and that is also a sp3 group, and it has a bond angle of approximately 105 degrees, which makes it a bent group. In the pink, we are going to go to pink before we go to oxygen, but in the pink, we have our sp2 carbon, and it has a bond angle of 120, which makes it a trigonal trigonal planar. Sorry. It is a sp2 carbon because it is connected to the OH, which would make it S. It is double bonded to oxygen, which is 1p, and to another carbon, which makes our second P, so sp2. In the teal color, we have the second oxygen that is present, and we are going to continue calling it just oxygen, and this is our sp2 oxygen. making it linear because it is double bonded to the carbon and is only going one way and not bending in whatever other way. In the yellows, we have our two sp3 carbons, and they both have a bond angle of 109.5, which makes them tetrahedral. Functional groups. Over to the far left, we have the carboxylic acid group, which contains, or which would be our COOH, and here we would have our carbon. Here's our first O, which is the double bonded oxygen, and our OH group, which is just bonded to the carbon. In the middle, we have the NH2 group that is connected to our chiral carbon, which makes it a primary amine, and later you'll see why this wedge here is important, but it is a primary amine. Here to the far left, we have our sulfur-containing thiol group, and this is our HS group. And we will see where that sulfur comes in to be important. These are the carbons within cysteine. On the far right, connected to the double bonded oxygen and the OH group, is a primary carbon, but this is considered a vinylic carbon because it is directly connected to a double bond, which would be our oxygen. In the center, connected to our amine group or NH2 group, we have our secondary carbon or secondary allylic carbon because it is one bond away from a double bond. On the far left, we have our primary carbon, which I have mislabeled as a secondary carbon. But since I am presenting, I'm making sure to fix that mistake and say primary. It is a primary carbon because it is only connected to one other carbon. Same with the vinylic, making them both primaries. Here we have the IR spectrum for cysteine, and on the far left we have the single bonded OH group that is part of the carboxylic acid, and that's our hydroxyl group, and it is around 3,200 to 3,600 centimeters to the -1. And here next to it we have our SH, our sulfur-containing thiol group, and that is supposed to be near, or I drew the circles as close as I can to the 2,500 to 2,600 centimeters -1. So they are pretty close to each other, but because of the shapes, this is as close to accurate as I can be. But I'm making sure to give those numbers to you. Over here, we have our CO bond for carboxylic acid, which would be our double bond, and this would be from 1,600 to 1,700. And then over here is our amino group, and that is the NH group specifically. And we can tell it is because of these ridges here that are a little bit farther than they would be if you were to look at an IR spectrum that does not contain an amino group. So that would be our amino group, and carboxylic group, thiol group. Okay, now for the IUPAC name. The full name of cysteine is 2R2-amino 3-sulfonyl-propanic acid. But because for presentational purposes and because I want to properly explain why it would be a 2R group, I am only explaining the name basis of our IUPAC name on this for now, before I go on and continue with the 2R. So here it is called a 2-amino because the amine group is connected to our second carbon, which, if you hadn't noticed, I'm going 3, 2, 1 because this on this side, this carbon has the most children, as we put it in our Mr. Salmani's class, connected to it, which means that it has priority over the other carbon connected to the sulfur. So it is called a 2-amino sulfonopropenic acid. And over here we have our sulfonopropenic, which I am now noticing should have had a 3 before its name. So it should have been 2-amino 3-sulfonopropenic. And so I'm making sure to point that out as I go, point out my mistakes. And so that is, again, 2-amino 3-sulfonopropenic. Okay, so what's really going on here? So here I've drawn this model myself to best indicate what's happening here. And so here we have the cysteine, which, fun fact, cysteine's name can be spelled as both cysteine with an E and cysteine without the E. And scientists use these slight differences in name, to show when this specific molecule has been oxidized or not. So pre-oxidation, the name contains an E, and that is where we see the HS complete before it becomes oxidized, and our hydrogen leaves that sulfur, which makes it a sulfur with a negative charge. Okay, so this is where it becomes oxidized and loses that hydrogen. This arrow is pointing to the next part, where that cysteine would then find another cysteine that is in close proximity, and since both of them would be, in this case, or in this example, oxidized, our sulfurs would be attracted to each other, and that would complete the disulfide bridge, making it this long chain, which is then considered, at this point, considered cysteine, but I've been saying the names as cysteine and then to cysteine. But that is what's truly going on, and because there's so many different ways that cysteine can be used, there's abundance of uses for it, and this oxidization is a very important factor because of the disulfide bridge. Why is cysteine highly reactive? Cysteine is highly reactive because of its high nucleophilicity, meaning it readily donates electrons to form bonds with electrophiles, or electron deficient species. The thiol group SH is also considered highly reactive due to the sulfur itself, and thiol groups are less electronegative than OH groups, meaning that the bonds between it are weaker and more easily breakable. Sulfhydryl groups are easily oxidized and more polarized than oxygen, which makes them a better nucleophile, like I said, and more able to participate in chemical reactions because they are more ready to donate and accept electrons. Due to being so reactive, cysteine has multiple biological functions, which is why it is used in the detoxification of our livers and in our hair, skin, etc. It is also highly reactive because of oxidation. The thiol group can be easily oxidized, like I said in the last slide, forming disulfide bonds with other cysteine residues. There is also a factor for its reactivity in the pKa value. Cysteine's thiol group has a pKa value close to the psychological pH, meaning it exists in its reactive dialate form of S negative under normal cellular conditions, which would in turn enhance its reactivity. So it can exist as its SH form or its sulfur negative charge form. Chirality. So here we have our chiral center, and it's considered our chiral center because it is connected to 4 different strands, and that is our hydrogen, NH2, and then our 2 carbons, or 2 carbon chains that are a carbon connected to SH and carbon connected to, or we can just call it our carboxylic group. So it is connected to our NH2, carboxylic group, hydrogen, and then other carbon chain containing sulfur. Okay, so how would we go about this? We would go about this by ranking them in terms of who is the strongest, and the strongest would be nitrogen because of its placement in the periodic table. So our NH2 would be labeled number 1, while our hydrogen is labeled number 4, with it being the smallest and number 1 on the periodic table. Next, we would look at the carbons that are connected to our central carbon. And since the carbons are both equal, we must look at the next possible part of the strand. And so we would be comparing our sulfur to our oxygens. And although our one carbon has 2 oxygens, that does not make it stronger than the sulfur. So we would go from our nitrogen to our sulfur and then the oxygen because of sulfur's placement in the periodic table, and which gives it priority over the oxygens. This dark wedge on the NH2 also means that it is facing us rather than facing away from us. If the NH2 had been a dashed line, or as I've drawn here for our hydrogen, an empty wedge, then that would mean that it would be facing the back, meaning that this whole reaction, or whole molecule would have to be flipped in order to accommodate for chirality and make sure that the NH2 is to the front, since it is the strongest of the 4. And as we can see here, it is going in a clockwise motion, making it R. That is, and which is why in our IUPAC name, the complete name would contain the 2R because it is connected to the second carbon within the chain, or within the longest chain. So 2R, and then the name was IUPAC. Enantiomers. The enantiomers of cysteine are L-cysteine, and this is a naturally occurring form found in proteins in the older DL system. It is referred to as L-cysteine, and in the RS system, it is designated as R-negative cysteine due to the priority of the sulfur atom and its side chain. So you see that the sulfur is given the priority, and the NH2 here is that solid line, and this again is a naturally occurring cysteine. On the right, we have our D-cysteine with a R configuration, and it is human synthesized. And this is a mirror image of the L-cysteine and is less common in nature. It is referred to as D-cysteine in the DL system and S-cysteine in the RS system. So, and again, another mistake that I have made, and I do apologize for that. It is considered an S configuration, which I am now noticing. So how do we use it? Because of the ability to create disulfide bonds, or cysteine with no E, cysteine is crucial. It gives structural stability to proteins and aids in tissue repair. The synthesis of glutathione also relies on this, and glutathione is a antioxidant, and cysteine is the precursor to this, and it makes it able to protect cells. And again, like I said, it is a major antioxidant within the body, which protects the cells from oxidation. Cysteine also helps to remove harmful substances or toxins and helps in other metabolic processes. And here we have that example of the changes that cysteine undergoes from this homocysteine plus serine, and this is one of the reactions that cysteine can undergo. The future of cysteine. So what is the future of cysteine? Cysteine can be possibly used as a potential cancer treatment because of its ability to form disulfide bonds and to partake in redox reactions, and which makes it vital in maintaining cellular redox balance. It is also, like I have said time and time again, a very important antioxidant defense, and cysteine is already a good antioxidant. So in the future, the helpful components of it may be enhanced to create a more essential or more concentrated supplement against oxidative distress. Another thing, which because I haven't mentioned much of its plant side use, it can be important in agriculture because of its antioxidant properties, and in turn improve build crop resistance against conditions like drought, where there's so much oxygen and not enough water for the plants. So in conclusion, the polarities of molecules and bonds within cysteine make it highly reactive, as well as the sulfur and the weaker bonds that it contains. Cysteine's unique chemical properties make it valuable for future medical uses like cancer treatment and environmental applications. So no more plants due to drought, which would help us a lot, especially in places like the valley where we do undergo a seasonal drought, and in times where there's too much heat and we don't have rainfall. It is really hard to keep the plants alive when we don't have rain. So having cysteine or having products that can help keep plants alive longer without needing to be watered would really help us, and especially places in the world where they don't have access to sustainable water sources. So thank you for paying attention to my long presentation, and I am sorry for those mistakes that I've made. Over here we have our references. But that is it. Thank you.